In the last segment, I introduced like dissolves like, where I have something very familiar like table salt. And I'm not sure if you can see that table salt. We know intuitively when we take that solid table salt, we put it in water, we stir it around, we can get it to dissolve. Okay? And you don't see the crystals anymore because the sodium and the chloride ion separate, and then once you stir it around, it just looks like water. We know the sodium chloride is still there because if we tasted it, it would taste salty. Well, what happens when we have something that's not an ionic solid, something that we don't know what it is, in liquid form? What happens when we put that in water? Well, we have to ask ourselves, will there be attractions? Okay, so again, we have to be able to draw our Lewis structures. Okay, so I'm going to put a curlicue around this as my solute. And then I'm going to put some waters around this. Okay, so I'm showing that this is the solute because there's fewer of them. Water is the solvent because there's more of them. Okay, so in order to figure this out, you have to draw your Lewis structures and then you have to draw polarity. Because you're not going to find this on a solubility table because it's not ionic. There's no ions here. This is a carbon compound. Carbon is not ionic. Okay? Partial negative, partial positive, partial positive, partial negative, partial positive. This part is not polar. We have a partial positive here on the carbon, but it's so small I'm just going to ignore it, okay? Really teeny. Partial positive, really teeny. Partial negative, positive, positive. Okay. So the question is, will these mix? Will there be attractions between our solute, which is got partial negative and partial positive, and our water, which is partial negative, partial positive? Well, when I put these together, yeah, they will mix. And the reason that they will mix is because there is an attraction. Let's see, we're going to kind of take the long way around. Partial negative, partial positive, partial negative, partial positive. Okay, so these don't hydrogen bond to anything because they are not charged. Okay? By the way, what I mixed was coffee and water, okay, for the purposes of the demonstration. This is something you would never want to consume. Okay, so the solute, charged, solvent, charged, yes, they will mix. So when your solute and solvent are substantially alike, yes, they will mix. Okay? Now, my CH4, if I try putting that in some water, I'm going to put just an extra water over here. Okay, so the question is, well, where is the polarity? Okay, where am I going to have some polar bonds in a polar molecule? Carbon-hydrogen is not polar, but our water is. Okay, partial negative, partial positive, partial positive, negative, positive, positive, negative, positive, positive. Okay, so what that means is there's nothing about this that's going to attract to the water. Okay, there is no attraction at all. None. Okay, so what that's analogous to is I've got my water here. I've got my CH4 here. I'm not sure if you can see it. It's not going to mix. It just sits there. Okay? Not mix at all. Okay? So, Our solvent is charged. Solute is not charged. Will they mix? No. However, the water will continue to attract and mix with other waters, and that is why our water remains as a liquid at room temperature, which of course is what we want. Okay? So this is very, very visual. If you wish to try this at home using your own visual aids, I would encourage you to do this, because your ability to move forward on this, especially when you move into the biological sciences, hinges on this basic idea of how do molecules work in a water environment. And just as a tangential FYI, the human body is about 50 to 60% water at any given time. Okay, so if you're going to be quote unquote compatible with the human body, you have to be compatible with water. By the way, the only difference between this molecule and this molecule is that this one has an oxygen. So the way I got the carbon compound to mix with water was that I added something that was polar or electronegative to the carbon compound. All right, so now I'm going to switch gears just a little bit, and I'm going to say, okay, I'm going to create something that is non-aqueous. So I'm going to take my CH4, and I'm going to mix it with C2H2. And I'm going to show that my C2H2 is my solvent by showing more of them. Okay? Now, no polarity here, no polarity here, no polarity here. Okay, so my answer to this is yes, they will mix. Yes, they will mix not because they attract, but because they don't repel. Okay, so that in my house where I have visual aids would be sort of like, let's see what I can grab super quick. Okay, so for lack of better analogy, my pencil dispenser. You can see my house is a wreck. Okay, so my marker is different from my pencil, my scapula. I mean, what house isn't complete with this without a scapula, right? And my ruler and all kinds of junk, right? It's not that they are attracting, it's just they are coexisting. Okay? It's not that they are attracting, they're just coexisting. And so that is how we can say that nonpolar will mix, not because they are attracting and sticking together like super glue, but because they're not interfering. Okay? Now the pattern. If solute and solvent are alike, yes, they tend to mix. If they're not alike, then they don't tend to mix. Okay? Now this is hugely important to understand. Huge, 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 huge. Okay? Because in a beginning class, we just give you, yes, they'll mix, no, they won't mix. And then as you move on, especially in biochemistry, if you choose to go right to biochemistry, there's this whole thing in the middle that says, well, sort of, well, kind of. Yes, when we mix these things together, they do weird things. And that's how we get a cell membrane. With a cell membrane, we can get a cell. When we get a cell, we can get things that move in and out of a cell. We have a nucleus, and then we can have a living particle. Okay? In the next segment, we'll talk about what happens when you try to apply these ideas in practice.